Everyone, and it is indeed my pleasure to have Professor Alexander Pyatenko, who is a professor at National Institute of Advanced Industrial Science and Technology, which is AIST in Japan. Professor Pietenko, he is graduated from Moscow Institute of Physics and Technology. He had his PhD degree in chemical physics in 1981. So it's like you can see, he has quite experience at the same university.
Quite old.
Right. And he had worked as a researcher, senior researcher at Institute of High Temperature, Russian Academy of Science since 1993. He worked as a senior researcher at National Institute of Advanced Industrial Science and Technology in Japan. Since 2001, his main research interests are nanotechnology and laser processing. He published many papers in high rated journals, gave invited lecture at several international conferences. He is a specialist in nanoparticle synthesis, modification, and resizing using laser techniques. So today, what he is going to talk about some nanoparticles, where in the first that remains one of the most important subject in nanoscience and nanotechnology, and a variety of different nanoparticle can be produced by different chemical and physical methods, whatever it is available now. So Professor Pietenko is going to, talk all, those details about the nanoparticle synthesis. So it is indeed pleasure on behalf of Academy of Nanotechnology and Wastewater Innovation, together with IEEE Nanotechnology Council South Africa chapter, to have Professor Pietenko to give this keynote lecture today. And obviously, like I can see, still people are going to join. Some of them already sent some apology. They have some network connection as well. But I think during the course of time, actually, they will be joining. And I am, very thankful to you, Professor Pietenko, to join us and, to bless this occasion in terms of like sharing your idea. So now, again, thank you very much, and over to you.
Okay. So first, thank you very much for inviting me. Thank you very much for this short introduction. So I will share this. Okay. And okay. So I will start my lecture. Thank you very much. So first of all, let me introduce briefly. Already the chairman introduced me there, and so very full, very nice introduction. But I would like to say few general things. I am Russian, so I was born in Russia and graduated the Moscow Institute of Physics and Technology. After that, moved to one of the biggest scientific institute in Moscow and work about 10 years. So after that, we have let's say, really small collaboration with Japan. And some people ask me still, how you moved to Japan from Moscow? What's happened? How you, at that time, I was not so great researcher, still 10 years working in science and technology. So generally, my answer on this question, how can I move to Japan? I said, I don't know. This is quite occasionally. Nobody knows. So we have this, as I said, small collaboration. After that, the men with whom we collaborate, one called me and asked, do you want to go to Japan? And I said, what means? He said, for a long time. And I said, what means a long time? He said, I don't know. So I discussed with my family, and my wife said, please ask him strictly, what means a long time? Long time means 1 year, or means 1 month, or 10 years. I tried to ask him several times the same question. what means a long time? And he said me, I don't know, really. And this is, after long time living in Japan, I understand. This is Japanese character and Japanese bureaucracy, maybe. Because before my coming, they couldn't decide it, what kind of position they proposed me, and did not decide it. This position will be permanent or not permanent. Only after I come to Japan, and after half year maybe, when they became familiar with me, they made a decision, give me the permanent position of senior researcher in this institute. So I was very happy, of course, at that time, but before that, I was very confusing. Nobody said me for long time, do you want to go to Japan for a long time? I remember this situation was very confusing. Okay, so first I came to the, not to Tokyo region, but to Sapporo. Maybe you know, Sapporo located in the North Island, Hokkaido, very large island, Hokkaido, the north part of Japan. And in 1980, the Winter Olympic Games was in Sapporo. And very funny situation. Several times I explained to some people when they asked me, Sapporo? I said, you know, Sapporo, Olympic Games and so on. And once I remember, I tried to explain this thing about the Sapporo to a relatively young lady. She said me, where are you living? I said, Sapporo, do you know Sapporo? And she said, So, oh, Olympic game, do you know? The Olympic game was in Sapporo, 1980. And she said me, sorry, at that time, I didn't born yet. so I confused and recognize I'm a little bit old man. Yeah, sorry. So after about 10 years working in Sapporo, I moved to the Tsukuba area. And on first slide, you can see the image with my title of presentation, my name, and so on. You can see the image from this institute.
Sorry,
rather huge institute.
Sorry, Professor Alexander, we can't see your slide.
Not yet. So maybe you introduce by yourself from my email this slide. Not, it's difficult.
Okay, can you try again? Maybe close it and then try to open. Because
okay, I close. Yes.
Yeah.
Close now.
Yes. Now you can
open share.
Yes.
Open and open this one. This one. Did you see? No, something.
Yes, now it is.
Just for applicants
okay.
All low medium income, lower income countries and the lower middle income countries. Is that?
So it's better now. It's better to push F5, yeah, to make a full screen.
Yes, yes.
Okay. F5. Oop. Not doesn't work.
It should be somewhere down there, you know.
Nope.
But it's fine. You can carry on like this. Yeah, I can see. So you can carry on like this. It's okay.
Okay. So let's use this one. So this is my first slide with my title, and on this slide you can see maybe not good because this is not full screen, but you can see the image of the territory of my institute, AIST. So this is the National Institute of Advanced Industrial Science and Technology, and it's located in Tsukuba City. Tsukuba is very special city, not only in Japan, but around the world, I think. And about 60 years before, or 50 years before, I don't know exactly, the Japanese government decided to develop such scientific and technology city in forest area. So they found huge forest area in big Tokyo area, 60 kilometers far from the center of the Tokyo, and established several institutes and Tsukuba University in this area. Nowadays, after 60 years, please see, Tsukuba University is one of the best university in Japan, number 5 or number 6, I don't know exactly. And not only this Tsukuba University, and maybe Tsukuba University is not the main part, but we have several national institutes in this area, in Tsukuba area. Our institute, National Institute of Advanced Industrial Science and Technology, AIST, NIMS, National Institute of Material Science, also very famous recently, especially after developing nanoscience, nanotechnology. NIMS became the #1 in this area in Japan. And also, we have the JAXA, the Japan Space Agency, like a Japanese NASA. So recently, the Japan tried to prepare its own space vehicle. So I think government spent more and more money for the space program in Japan. So JAXA became more and more famous. And nowadays, people, when I ask something about Tsukuba, they say, okay, I know Japanese people. Because the JAXA located in Tsukuba. Most of people identify Tsukuba by JAXA now, Japanese Space Agency. Okay, so this is a few words about my working place, my institute. Let's move. So this is general slide, and of course, the people who know a little bit about nanotechnology recognize easy. So at the left, we have the graphene nanostructure, very nice photo made by STM, I think. Nanotubes, next, and colloidal nanoparticles with different colors on the right. So I would like to say, all these most 3 famous things which characterize the nanotechnology and nanoparticle belong to the nanoscience, not to the nanotechnology. Because, let's think, nanoparticles. We produce nanoparticles in my laboratory. We produce per day maybe micrograms amount. It's possible to produce if we concentrate on the production. Maybe it's possible to produce 10 grams or few tens grams, something like this, not kilogram. It's impossible for me to produce 10 kilograms of nanoparticle. The same situation with graphene. Graphene became nowadays, graphene is very famous science material. Yeah? Many people in different laboratories around the world try to use the graphene in their research. But how much the company produce this graphene? Not gram, microgram, I think, less than microgram, and very expensive. The same thing about the nanotubes. There are two types of nanotubes: single wall nanotubes and multi-wall nanotubes, not single. And there are huge difference between these one. The multi-wall nanotube became the nanotechnology, yeah, because some company already could produce the tons of these nanotubes, and the using of this nanotube is very wide around the world. But this is not completely, how to say, not so good controllable object of nanoscience. The company which produced this multi-wall nanotube could not control the property exactly, and they are not interested of exactly physical chemical property of this nanotube. Most interesting for the nanoscience is a single wall nanotube, but this single wall nanotube could be produced, let's say, also less than 1 kilogram, maybe 100 grams. If you succeed to produce 100 grams of single wall nanotube, it will be already great result. So I would like to say, maybe some people like to speculate about the nanotechnology, but really, most of the people who work in nanoscience and nanotechnology belong to the nanoscience, not to technology. It's exactly concerned to our laboratory, our group. We work in exactly nanoscience. We are interested in physical, chemical, material property of the nano object. And if you would like to ask me about the real application, and not for scientific application, but more wide application, my answer will be, I don't know. I don't know real application of the nanoparticles for industry, for example. And I remember when I started 20 years before, I was not so great specialist at that time, still started working in nanotechnology, nanoparticles, and some of my colleagues listen that I produce nanoparticles said, oh, I know the application of nanoparticles. So I said, what? You produce the silver nanoparticles? I said, yes. One of my favorite objects is silver nanoparticle. He said, in hospital, I know, it's better to paint the wall by silver nanoparticles because the silver nanoparticles strongly working against the microbe, bacteria, and so on. I said, oh, it's very good idea, but unfortunately, we produce less than 1 gram of these nanoparticles. So if you want to paint wall in hospital using my nanoparticles, we have to work not 100, 1,000 years for this one. So it's impossible. So please think, of course, our final purpose to produce the nanoparticle. Produce controllable nanoparticle with controllable properties. But our rate of production is very, very small. So due to this very small rate, it's really impossible to say about the nanotechnology, just about the nanoscience. Okay, let's move next. So on next slide. No? It's okay. Did you listen to me?
Yes,
I said,
yeah,
okay.
All going good. Thanks.
Okay. And you could see now my next slide, yeah?
Yeah,
with laser
ablation.
Okay. So on this slide, I show the main idea how to produce nanoparticles by using the laser ablation, laser irradiation. So I have to say, this is not our group idea. We found this, not exactly this figure. Maybe this figure we modified and made more beautiful and so on. But we found this figure from the journal published 30 years before, something like this, 10 years before we start to work. And already at that time, some people had the idea that if we irradiate, put some metal plate inside of the liquid, let's simply say it, inside of the water, and irradiate it by very good focusing laser beam. So you see, using this scheme, I show that the laser beam first was parallel, came from the output from the laser, and finally, very good focusing on the surface. The spot size is the order of not millimeter, 10 micrometers or 100 micrometers, something like this, much less than millimeter spot size. So we have to concentrate all the energy of the laser beam in one point. So after that, we produce plasma. Not simple process. We produce the plasma plum above the surface, and in this plasma plum, nanoparticles finally formed. So if we put, let's say, silver, because research about nanoparticles, all the research about nanoparticles, was started, let's say, about 30 years before, when the people start talking about the nanoscience, nanotechnology. And at that time, the first object was silver and gold. So the people tried to produce silver nanoparticles, gold nanoparticles. For this purpose, they put the silver or gold plate very small. Not image that this is 1 kilogram of gold. It must be the very thin plate film of the gold or silver. So the price is not so huge. We did it in our laboratory, so we ordered a lot of this target from silver gold pure. Price is not so high. And after that, put it in pure water and irradiate by laser beam with focus. Laser beam must strongly focusing in one point on this target. Okay, after that we produce the nanoparticle. It was one of the first idea, how to do it with laser. And this is a result. This is my result, which I produced about 20 years before, maybe. A little more than 20 years before. 25. So when we start to repeat it, such a very simple processes by ourselves, and when we observe the result of our production by TM microscope, electron microscope, so we observe this picture. So you see, really we produce the nanoparticles. The size of these nanoparticles is nanometers, not micrometers. But the range of the nanoparticle change from several nanometers up to the 100, 200 nanometers. So huge range. It need to, so after producing this result, not immediately, but we decided it's need to think what to do with this nanoparticles. It's need to do something because, yeah, it's good. We produce the nanoparticles, but it's impossible to characterize these nanoparticles by size. So what to do next? And at that time, we check other process. And this process, pure chemical synthesis of nanoparticles. This process, according to the literature, the first people who proposed this chemical reduction synthesis of nanoparticles was Turkevich, and he published his result, unfortunately, in not so famous journal, but in 1951, so 70 years before, 71 years before, he already proposed. Of course, at that time, nobody said about the nanoparticles, and I forgot now how he said about the final process, final product. It was nobody had said about the nanoparticles at that time, so he used some, I forgot, sorry, some different words for this nanoparticle. But really, when we check this process and final result, it was a nanoparticle. And he produced this nanoparticle, silver, you see, this is the silver, using the first silver nitrate, very simple chemical compound, which used in classical photography, silver nitrate, silver NO3. So this is a liquid. By using very simple chemical procedure, just heating with citrate. Citrate is a simple organic compound which had a reduction property. And you see, because in silver nitrate, we have a NO3 minus ion and silver plus ion. So if we want to produce from this silver plus ion neutral nanoparticles, first we have to reduce this plus ion. So we use, not we, Turkevich proposed to use it for this purpose. Citrate, very simple organic compound, with reduction property. And not just only reduction. It was in his research, Turkevich didn't emphasize that he found a very unique, very unique reduction agent. Nowadays, the people use a lot of different reduction agents, but still now, I think, remains one of the beautiful reduction agent for the simple production process, because they not only reduce the silver plus ion to silver, which after that, due to the aggregation, produce the nanoparticle, but he had a double role. Reduction is the first, but next, on the surface of these nanoparticles, citrate coats the surface and prevent the nanoparticles, final nanoparticles, from the final aggregation. Without this reduction, or not reduction, surface prevention agent, the agglomeration process continue and continue. So we produce something huge piece of the silver, not nanoparticles. Nanoparticles will be continue to aggregate. So our result will be not so beautiful, bad result. And okay, we checked, studied this paper of Turkevich about the chemical production and tried to repeat it. So we repeat it very easy, because I again said, the chemical procedure is so simple. We just use the liquid silver nitrate. This is very simple chemical reaction. This mixture, pure water nitrate, mix it and heat it up to 100 degree, just normal, using the normal mixture. With mixing, of course, using the stirrer, chemical stirrer. During 1 hour, we produce this result. But you see, this again, after we producing this result, and first, when we make this chemical synthesis process, we see, oh, after 1 hour of heating, of boiling, our colloid changed the color. First, it became transparent, no color, and finally became the typical silver color, reddish or something like this, like this, yellow reddish, something like this. So we were sure that it was silver nanoparticle, but when we check our result by electron microscope, so you see, we produce this result again. The result is not so beautiful. We produce some huge particles with size about 100 nanometers, and instead of this huge particle, and this huge particle had different shapes, you see, not spherical particles, of course. Some nanoparticles look like nanorods. Other particles look near the spheroidal particle. Some particle looks like a good sphere, but some particles ellipsoidal shape and something like this. But again, instead of this huge particle or large particle, we produce a lot of very, very small particles. You see on this figure, with size about 5-10 nanometers. So again, it's impossible to make what kind of particle we produce. This is a mixture of the large particle with different size and very small particle. So it's need to do something with this again. So not using the laser ablation, by using laser ablation, not by simple chemical synthesis, we could produce a good result. So we have to think what to do. Okay, next. We try to use previous result, this one. Result of chemical synthesis. So nanoparticles produced by chemical synthesis. And try to ablate this solvent by laser, our laser. After 1 hour of ablation of this colloid, we produce this rather good result. You see, now only small particles we observe, and particle size could be characterized by the very sharp particle size distribution. Average size about 3 nanometers, plus minus 1, something like this. Here shows the histogram of the particle size distribution. So very good result we produce. But next question. Okay, we succeeded to produce very small particles with the size 3 or 4 nanometers. But what to do if we want to produce different size of the particle? If we need 10 nanometers, 20 nanometers, 30 nanometers, how to behave? So we will continue to think. And
Prof.
Yes?
Is your slide, you are still in laser ablation slide?
Yes.
Okay,
Yes.
no, that's fine, because I thought like it's not moving. Thank you.
Mm-hmm.
No, you carry on.
So this laser ablation next.
Yes.
Laser ablation here. Next is result of laser ablation. You sure? You see here? Result of laser ablation, nanoparticles.
Now we are still in slide number 3.
Number 3. Wow.
Yeah.
This one.
It's not moving. Maybe
in my computer.
Yeah, I can do it from my side.
Okay.
Okay, just a moment.
But another possibility.
It is visible.
Another possibility I can use. Oh, no.
Not yet.
Okay, so what it's better to do? To stop sharing or continue? Open share. Just now it's not open. Okay. This one. And this one.
Yes, we can see the slide, the first slide.
Mm-hmm. Could you see the laser ablation slide next? Not? Maybe so slowly it works, huh? This is the first slide. This is the next slide. Could you see this one? This one, laser ablation.
Prof, we can only see the very first slide.
So it's a mistake. Yeah? My computer shows that I share my slide here. Yeah? Okay. Okay. Mm-hmm. What's need to? It's okay now. Hop, hop, hop. Hop. Yes. Yes, 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 yes. I heard, but I couldn't see you. Okay. So close completely, eh? Presentation. Okay.
Hello? Am I audible? Sorry, I think it's completely stuck. I'm not able to hear nothing.
I can hear you, Prof. But I think Prof, I can't pronounce this name. Prof Alexandra is logged out and I'm trying to admit him, but it keeps on not admitting him.
Professor, you are not able to hear. I mean, we are not able to hear you. Please check your microphone.
Yes. Okay. So I can try to open share again. Okay. Okay, okay. I'm waiting for you. Mm. Mm-hmm. Okay. So I will try to share, yeah? Okay. Okay. Share. Try this one. Okay. Coming. Okay. So how about F5? Okay. Working. I push F5. So now in my computer full screen.
Okay, that's fine. You can carry on. Let me just ask with the audience. Smiley,
Okay.
can you hear me and Professor Alexander?
No answer.
I
Yes.
can hear and I can see the
Yeah, yeah.
slides.
Yeah, that's fine. That's fine. Now he is coming. So you can even see the slide, Smiley?
Yes, I can.
Okay, no, that's fine. Thank you. Yes, Professor Alexander, now you can proceed to the next one.
Could you see next one?
Yeah, can you move your slide?
Okay. Now laser ablation.
Yeah, but still it is page number 1. Sivani, can you confirm to me?
It's still it is still slide number 1.
Yes.
I moved number 3 already.
Okay, no, that's fine. So can you do the stop sharing so that I can start from my side?
Okay. So it's better to close sharing.
Yes. Yeah,
Okay.
just say stop sharing. Yes.
Okay. I stop.
Okay, let me just try to do the sharing from my side.
Yes, it is visible.
Okay, now.
I saw the first. Okay. Okay.
You were here?
Laser ablation. I saw. Yeah. Yeah.
Okay, so
Yes.
now you will guide me like where to stop and where to stop.
Okay. 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 So already I talk you. Unfortunately, maybe you didn't saw first, but I talk you about this slide already. So this is a electron microscope image of the our result of laser ablation. So in result of laser ablation, we produce this mixture of different particles. All the particles look like spherical, but size range from few nanometers to 100 or 200 nanometers. So it's need to do something. Let's move to next slide. Next slide, please.
Okay.
No, I couldn't see. Next slide.
Is it not moving?
No. Ah, okay, okay, it's moved now. Okay,
Right.
so just very slow. Okay, so this on this slide, I show the very classical work of Turkevich. He's proposed the chemical synthesis of the silver nanoparticles using the reduction agent, the citrate. And I already talked about the double roles of citrate, not only just the reduction agent, but the kind of surfactant, surface prevention from for the further agglomeration of the particle. So using this chemical technique, Turkevich in 1951 succeeded to produce the silver nanoparticles. And as I said, of course, he never mentioned about the nanoparticles. At that time, it was not popular, said nanoparticles. Okay, let's move to the next slide. Okay, so when we try to repeat it, result of Turkevich, and when we observe our result by electron microscope, we observe something like this. The result looks not bad, but not so beautiful. We again produce the mixture of the large particle and very small particle. Very small particle size of a few nanometers, very large particles, 200 nanometers, something like this. So it's need to do more. Okay, let's move next slide. And this is the result. First, our idea was, let's irradiate not surface, like a laser ablation, solid surface immersed in the liquid, but let's ablate colloid. We produce already nanoparticles. Let's ablate, using the same technique, our nanoparticles in colloidal form. So using such idea, we produce these nanoparticles. All nanoparticles is very small, and you see very uniform size, about the 4 ± 1 nanometer, something like this. But we succeeded to only produce very small nanoparticles. So the next question, if we need to produce a different size of nanoparticles, what to do? So we have to think next. Let's move next slide. So I stopped on this. Okay, so as I already told you, in literature discussed very wide the first process, laser ablation in liquid. So this process, when we concentrate laser beam in one point and put this one point on the surface of the solid surface immersed in the liquid. In case of silver nanoparticles, we put the silver plate just in water with citrate. So when we ablate it, we produce a nanoparticle. Okay, but we have the other possibility. Let's try to ablate colloid with nanoparticles with non-focused laser beam. Why we think non-focused? Because if we concentrate laser beam in one point, so the probability of interaction of this laser beam with nanoparticles becomes very, very small. Please image. The laser beam concentrated in one point. So instead of we mix our colloid, so our particle moves, but the probability that our particle, different nanoparticles meet end of laser beam at this point will be very small. So it needs a long, long time for ablation. So our other idea, let's try to ablate this colloid by non-focused laser beam and see what to be. Okay, let's move to next slide. Okay, using this idea, first, we produced many interesting results. And first, our result was produced experimentally using different colloid, different initial nanoparticles. We ordered these nanoparticles from Aldrich Sigma company. Already, Aldrich company, Sigma, some people know Aldrich, like Aldrich, other people know as a Sigma. This is the #1 company which produces different chemical around the world. So it's possible already 15 years before. Some nanoparticles from this company. Of course, the cost is not so small, but not so huge. For example, if we ordered the silver nanoparticles for 10 millimeter of the silver colloid with nanoparticles, we have to pay the $100, something like this. Nowadays, I think the price came down there, essentially. Okay, so we try use the commercial production of nanoparticles, prepare the colloid with these nanoparticles, and try to ablate this colloid by non-focused laser beam. So our result shows on this picture. We was surprised. We produce spherical particles, very, very nice spherical particles with rather small particle size distribution. So it's possible already said, this particle is spherical and particle size could be the, for example, 320 plus minus 50. So this is not bad result. Okay, let's move next. Okay, so this is another result with silver nanoparticles. Okay, let's move next because not so many times. Yeah, here we have the, after 1 or 2 years of experimental work, we succeeded produce completely spherical particles. So you see in insert of each slide, we show the large magnification of single particle from this colloid. So all particles is completely spherical. And size of this particle is rather uniform. And we did it for different material. And some of this material is very, very important as a material. For example, zinc oxide, titanium oxide, copper oxide. Very, very interesting material for the technology and science. So we succeeded to produce this result for many different materials. And next slide, just I show you the zirconium oxide particle, single particle. It's completely spherical, and you can see, okay, let's discuss this one. All the particle is completely spherical, and this is kind of advertisement. I show the different materials, titanium oxide, zinc oxide, zirconium oxide, so on. Let's move next. Okay, okay, let's move. Okay, here. After 2 or 3 years of experimental work, or maybe 2 years, we understand that experimentally it's possible to find the suitable experimental condition, but for each material, it's need to find this optimal experimental condition individually. So first we have to spend 1, 2, 3 months to find the suitable condition. After that, we produce this result. So we decided it's need to stop only just experimentally study this process, and it's need to think about the theoretical part, theoretical description of this process. So again, searching the literature, we find some ideas, and using these very preliminary ideas, we constructed finally the model, particle heating, melting, evaporation model. Okay, let's move next slide. So the idea of this model is very simple. All the energy which particle absorb from the laser spent only for thermodynamics process with this particle. So let's say, if the energy which particle absorb from the laser not so huge, so what will be? Particle will be heating, just temperature increase. Next, if we increase the energy of the laser beam, so melting process could be started. Next, we increase the energy, melting could be completed and particle hit again. And finally, if our energy of our laser beam will be very high enough, evaporation process will start or could be complete. So we could finally exactly evaporate all our nanoparticles, produce the atoms, let's say, from our nanoparticles. So this is the idea. Okay, let's move next slide. And on the next slide shows the two main idea or two main conception which have to be solved for this model. So we have to understand completely thermodynamics processes with this material which particle consist of, and we have completely understand the light absorption process, how the particle absorbs the energy from the laser beam. After that, we have to construct completely the model. Okay, let's move next. So it must be the combination of the thermodynamics and energy absorbed by particle from the laser. Okay, on next slide, we just sorry, previous slide. Oh, yes, this one. On this slide, we briefly I show how the particle absorbs the energy from the laser beam, and this is very simple one, but one principal point we have to solve. The very small particles, nanoparticles especially, not absorb energy from light like a normal macro object. So if we put the macro nanoparticle, let's say millimeter particle, and eliminate this particle by light, so light will absorb by the particle, and cross section of this absorption process will be equal to the geometrical cross section of the particle. Yeah, this is very obvious process. But in case of nanoparticles, the cross section of absorption, energy absorption process could be quite different from the geometrical size. So first we have to find in the literature or calculate by ourselves this cross section, how the particle absorbs the energy. And this cross section, sigma, depend very strong on the size of the particle. Okay, next slide, let's move. This one. Yeah, fortunately for us, already 100 years before, German theoretician Meyer make such calculation, and it was at that time, how to say, very, very excited result. Not so many people at that time, 100 years before, about 100 years before, understand how this result produced by Meyer excellent, because at that time nobody think about the nano size of the object. Normally the smaller size 100 years before was about millimeter. Practically nobody operate with the micrometer size at that time, yeah. But for several micrometers, if we produce the particle 10 micrometers, for example, the cross section, absorption cross section, will be very close already to the geometrical size of the particle. Only when the particle became very small, nanoparticle, the result of the Meyer calculation became very important. And this paper published by me shows that using the macro characteristic of the material, N and K, absorption coefficient and refraction index. This is the electromagnetic coefficient, two electromagnetic characteristic of the bulk material. It's possible exactly calculate the absorption cross section for the different size of the nanoparticles. Of course, the MIA made this calculation for only for spherical particles. Nowadays, the people could change this calculation for ellipsoid, for nanorods, for example, and some other shapes. But 100 years before, they already made this calculation for spherical nanoparticles. And because we produce the spherical nanoparticles, so we applied directly the MIA calculation and try to use this theory for our calculation of the absorption to understand how the different size of the particle, spherical particle, will absorb the light. Let's move to the next slide. Okay, here is a very important part of our theory. When we calculate and estimate the energy dissipation time in two main processes, radiation, heat loss, and boiling heat transfer, because the particle put in the liquid, so if the particle temperature became very high, the liquid around the particle will boil, and we have every time the heat transfer between the boiling liquid and nanoparticles. So due to the heat transfer, the energy move from the particle to the liquid. And first, this is the simple radiation process. If the particle temperature became so high, so they irradiate the energy. Yes. So when we finally make estimation, numerical estimation for both main process, we was very surprised. Very nice result. So we could conclude from our calculation, our estimation, that this time is much larger than the time of the one pulse. Normally we use a nanopulse laser, and duration of one pulse is 10 nanometer. So you see, this time is much longer than the 10 nanometer duration of one pulse. It means during one pulse, no heat dissipation, no heat loss. So all the energy which particle absorb from the laser pulse spent only for thermodynamics process, heating, melting, evaporation, nothing more. No heat loss, no heat dissipation. But on the other hand, this time 10 minus 4, 10 minus 6 seconds is much smaller than the duration between the two pulses. And duration between the two pulses for YAG laser, for example, is 0.1 second. So anyway, all this time is much, much shorter. So it means that in time between the two consecutive pulses, the particle not just heating, melting, evaporated, but lost enough heat to cooling up to normal temperature. The heat dissipation time is much larger than the time between the two pulses. So in this huge time, the particle return to the initial condition. So this is a huge result. Without this result, it's impossible to construct our model. Let's move. Next slide. Here, finally, I would like to say about the thermodynamic itself. So for I said, it must be combination of thermodynamics and absorption of the light by particle. About absorption, we discussed how to calculate. Applying the MIA theory, we could calculate how the particle of different size absorbs the laser energy. And for the first moment, adsorption looks very, thermodynamics looks very obvious here. If we have the, for example, silver particles, yeah, if we said about the silver, what possibility we have for different thermodynamics? So first, our silver will heat up to melting temperature. After that, they melt. After that, the melt will complete it. After that, again, particles have to heat up to evaporation temperature, boiling temperature, and finally evaporate. But this only for simple metals, for silver, gold, for example. If we have a little more complicated substances, for example, copper oxide, we have already 1, 2, 3, 4, 5 different processes. Not just simple. So every time for each individual material which we try to use for production of this nanoparticle, we have to completely understand the thermodynamic. What will be with this material during the more and more absorption of the energy. Okay, next move. Next slide, please. Yeah. So finally, we construct such a kind of phase diagram. And in this slide, we show this phase diagram as example for copper oxide system. So on x-axis, we show the particle size, particle diameter, because our particle is spherical, so just diameter will be characteristic of the size. Yeah, and y-axis, we plot the laser fluence, which is a laser energy per unit square. Yes. So after that, you see, in this diagram, we saw the boundary between the different processes. It's easy to see that for different size of the particle and different laser fluence or laser energy characteristic, it's possible to understand what will be with nanoparticle. Nanoparticle will decompose or melt completely or evaporate and so, something like this. Okay, let's move to the next. So this is one of the main, no, let's say, one final result of our theory. And finally, we explain how we produce our spherical particles. So this is a combination of the agglomeration process and melting process. So to produce the spherical, exactly spherical particle, we have every time melt and melt and melt our particles. And fortunately for us, secondary process, agglomeration of the smaller particles in one agglomerate, help us. Particle became the more larger and melt and melt and melt. So finally we produce spherical particle with maximum size. So we explained this production. Okay, about the femtosecond laser, maybe let me have the possibility to discuss about the other our interesting result, including the femtosecond laser, for the next time. If somebody will be interesting to continue our joint research, continue our discussion, I will be happy and have to continue giving you a result about the femtosecond laser or some more new result which we produce, for example, in duetting process. But I think now already time is more than 1 hour. We continue our lectures. So not only me, but you, I think, a little bit tired. So I propose stop now. And I would like to say, finally, it's very interesting for me to make such presentation for you, because I hope for some people it will be interesting to start some collaboration with me, or maybe not now, but in a few years, next year or 2 years after that. we have the possibility to move. Some of you could move to Japan maybe, or I could move to Europe, some cities, and we discussed more friendlier and more easier without this stupid computer, this stupid program, and problem with slide and so on. So every time, it's my pleasure to have a new friend, new collaboration. So thank you very much for such possibility. Thank you.
Thank you very much, Professor Alexander, for making such a nice presentation. And it is indeed, it's quite informative. We experience a lot of, even the computer, as you mentioned, and obviously this whole discussion or the talk is all about like how we can work together, and that is the whole objective. We are here, and as you mentioned that we are going to have like more intensive discussion in terms of the deeper side of the project, where we can collaborate more further. And obviously, like I don't know whether you have been to South Africa, so you can visit us, and maybe you can walk with the lions, because African safari is very popular. And even for me, it will be quite good to come to Japan, because I have been there, and it is really a very good place and quite disciplined. And in the research, I think there is a lot of things to talk about, because the research is on the public platform, and the product is on the public platform. Whether you are going to talk about the television, I mean the electronic stuff, or whether you are going to talk about the auto vehicle, which is like cars and those kind of things. So everywhere, every part of the world, actually the the Japanese research is quite visible. And even in the acceptance, if you see that if something is wrong, they come directly and try to tell like this is the kind of issues are there, so we can recall her. So it is really very good thing. Now, before I open the floor, I just want to note some of the apology has been sent to me, and some of them, like remember Professor Gouris was right here, and then he also had another meeting to go, and then another one has the lectures actually, so he just moved. But I think they sent the apology that obviously like they wanted to attend you full, and then we can have the interaction. So obviously we are going to plan in the next phases, because this is just a beginning, so we can try to see that way. Then I don't know actually like how many, because only Professor Shivani and Smiley is there, and if you have any queries, can you just unmute your mic and you can speak to Professor Alexander. Prof. Shivani? Yeah.
Yes, thank you, Prof. It is such a privilege to go to the fundamentals of nanoscience and nanotechnology and learn new methods to make nanoparticles. Indeed, it was very impressive, and thank you for your availability to enlighten us with the basic concepts and the results, the beautiful results, and how one should actually look into the finest details of methodology, the preparation methods, and what to look into, what not to look into, what we must expect when we use any technique to prepare nanoparticles. Uh, I wish to ask you one very simple question. I have never used laser ablation technique so far to produce nanoparticles, but is it possible that we can prepare a mixture of nanoparticles together in one go using this technique?
Yes. It's the first result look very simple. So if you put some suitable chemical in this, for example, pure water with some citrate, and put just the plate of suitable material on the bottom of this box and irradiate by laser concentrated on this one, you easy show after 10 minutes or 15 minutes, the color will change because most of the nanoparticles had a characteristic color.
Yes.
So the color of your colloid change. So this result is good. After 1 hour, you see that your colloid will be saturated with color. But if you analyze using the electron microscope, the result, normally you could see the particles not homogeneous.
Yes.
You produce a small particle, large particle, spherical particle, not spherical particle, and so on. Yeah. So it's need to more, how to say, more precise doing something next with this one. So the, in spite of the first result looks very attractive and very simple.
Yes.
If you have a laser, just after few days you produce this result, colloid
Yes.
with nanoparticles.
Yes.
But the final result is not so beautiful. So you have to do next and next and next something with
Yes.
this one.
Yes.
So something like this.
Thank you so much, Prof. Now, hearing your answer, I have got one idea, which I will share. I mean, after this meeting or maybe later, but I've got some idea.
So I have a proposal. Please ask Ajay my email, and we could communicate by email, by Skype, and so on. Yeah.
For sure, Prof. I mean,
Yeah.
because
Okay.
I read one brilliant article very recently, and now when I hear your talk, I'm getting an idea very quickly in my mind, which I'm going to write it to you.
Thank you. Thank you. So
thank you, Prof.
I will be happy to communicate in the future with you. Yeah.
Yes, Prof. Anytime.
Okay. Thank you.
Anytime, Prof. Anytime.
Yes. Okay.
Thank you very much, Prof.
Thank you.
I think maybe next time I will be learning more about femtosecond laser, which again is, I think would be very interesting because I've never gone through this technique as well. But it would be very much interesting for us to learn more about the lasers and laser technology and even plasma. I don't know if you have done plasma.
Okay.
So I
Thank
think,
you.
Prof, thank you again for a wonderful presentation. It was really indeed enlightening because we need to get into the fundamentals of what we are doing. And thank you. It's a lifetime opportunity for us to learn something great. Thank you so much.
Thank you. Thank you.
Thank you, Professor Alexander. Thank you, Prof. Shivani. Smiley, do you have anything to say here?
No, Prof. I don't have anything to say, Prof. I was following. Thank you.
Thank you.
Okay, thank you very much.
Professor Alexander, I wanted to ask, like, I see with your presentation, you also prepared the titania. So this laser ablation techniques, what you are using, can you try to control even the phase of the titania, like whether it is going to be rutile, anatase, you know?
Yes.
So
yes. Very nice question, and we produce different phase of the titanium oxide. We succeeded, and in very similar experimental condition. Sometimes first we produce rutile, and
rutile.
Sometimes what the other anatase. Yeah, anatase or and finally when we more precisely analyze the very small difference between the experimental condition, we understand that how to change a little bit experimental condition, we could move from anatase to rutile. We could.
Yeah, thank you. Because in our research, what we are trying to do, I think it would have been good, like if we had some more researcher here. But the whole idea is like we are using this titania, and we are preparing via this titanium butoxide or isopropoxide, so those kind of precursor we use, and then we use the sol gel method mainly just to prepare. But obviously the application what we are more focused that we are going like advanced oxidation process, which is like a photocatalytic process, just to degrade some dyes or adsorb some heavy metal. So that is the wastewater what you talk in the beginning, like where we involve actually, So, but the whole idea behind our synthesis of this nanoparticle and embedding to some other metals, whether it is a p block metal or we are doping with the rare earth, so those whole idea is like how you can narrow down the band gap so that we can try to maximize the removal of maximum pollutants. So I see like there was a hand from Smiley. Maybe you got something to say. Smiley, you can go on.
No, I think you just asked my question because I wanted to ask on the related to the reduction of band gap, but also going to say, is it preferable to actually use the metals or the organics to do so? Because I want to actually shift the absorption of my titanium to the visible region so that I can use the visible light as opposed to UV, because if it is to be applied by many people, I might actually need to just use sunlight as opposed to having to buy lights that produce UV. Thank you.
Okay. So my proposal, Ajay, we connect, of course, in the future after this one, and I will prepare some suitable paper for you. We already published this result for Ratel and for Atanaza. So I will just find the paper. It's already maybe one paper 5 years before, but first paper about 10 years already. So I will find the paper and send you, and we will discuss after that how it's possible to use our knowledge in laser processing of nanoparticle applied to your process, because this is a little bit different.
Yes, and I think it's a quite good idea. I'm so thankful, and even I see what Ismaili has interacted with you. I think we can also learn a lot of things if happen to visit each other's laboratory in near future, because he's in the final year of PhD, and after that like he will be quite open. So the whole idea is like how you can share the expertise and how one can get the very good expertise actually, So obviously like with the experience, they can do a lot of things actually, and that is the whole purpose of meeting together to share ideas, to create the platform, and you can release in terms of like how to go more forward,
Okay. Okay.
Yeah. So that is the whole idea, and also the project what some of the researchers are trying to do actually, like making some mesosporous material and using again the phase change is quite important. Obviously with the titania as well, we are trying to play, but then we also play with the semiconductor material as well. So it's a lot of there, but I think that needs a lot of discussion. And I can see today you talk a lot actually, and I think since 10 o'clock you are available. So I have to really say thank you very much for you. This is the last thing I have to do. This is like with the note that we are going to connect very soon again, where we can bring very selective topics, obviously as you have mentioned, and then we can move forward. So on behalf of Academy of Nanotechnology and Wastewater Innovations and IEEE Nanotechnology Council South Africa chapter, I have to say thank you very much for availing yourself, sharing your knowledge, your ideas, and make yourself available for the next interaction and talk. I have to just say thank you very much.
Thank you. Thank you.
Okay, so now this meeting is adjourned.
Thank you, Prof.
Okay.
Thank you, Prof.
Thank you very much, and see you.